Good day everyone. Today I want to present about the electrical machine technique report about the small scale of the DC motor. We are from the group 1 section 5. This is our group member. First is the Ting Xing Yi, AE230061. Second is the Chao Ket, AE230005X, and me, Beji Cheng, AE230053, and the last is Chu Park Lee, AE230073. So the introduction, I will explain the one problem and the one principle of this project. In the technical problem in our project that have a bigger challenge in the design of the electrical machine is about the converting the theory concept into the practical implementation that perform reliability in a real world setting. So we conduct this project to address the technical problem of design and consulting a small scale direct current motor. So in the core challenge of this project is to ensure the motor perform parameters such as the torque, speed, and the efficiency with the theoretical conjunction value from both conversion design calculation and software simulation. So other than that is the discrepancies between simulator and the experimental outcome also need to identify analysis and minimum through carefully constructions, practice and interval perform optimize. And then the project principle is about a DC motor turn the electricity into a spinning motion using the magnet and the electricity. So when the electric current flows through the wire inside the motor on the rotor, so the wire are surrounded by the magnetic field from the stator permanent magnet. So it will create a pushing force that make the rotor spin. So a commutator constantly feeds the direction of the electricity in the wire as the rotor turning. So it will push strong and constant because they have the inertia. So the motor spin faster, it naturally generate a opposite voltage that called the EMF. So which increase with the speed and balance the battery voltage to reach steady speed. In the project, they call ideal were used to design a small DC, and it's really will perform like speed, power, and efficient. So that's all for me. So in design and constructions detail, the designing planning, the basic brushless DC motor with permanent magnet field. So we design the motor specification is about we use 18-volt battery as an input, and the second is core efficiency 60%. The rotor was wood with 45 turn of the copper wire. So in the descriptions of designing processing part, we need to do a simple calculations. So first we need to find the emitter resistance RA. So our copper diameter is about 0.51 mm. So we need to calculate the error is pi r squared. So we get the value is about 2.05 times 10 power of -7 meter square. And the resistivity of the copper wire is 1.6x times 10 power of -9 ohm meter. So we need to calculate the RA. We can use the R equal to rho L over A. So we get the value of RA is about the 0.41 ohm. And we can find the back EMF with the formula V minus I times RA is about 17.385 watt. So the speed omega we can calculate by the using back EMF over the back EMF constant is about the 286.5 per second, and the torque we can find kT times I is equal to 0.15 Newton meter, and the inductor's EMF checker is about 1.9 watt.
Good day, Dr. Awan. I'm Ding Xin Yi. Today I would like to present the design and construction details. For description and simulation works, we already conduct a simulation using a MATLAB. The motor's electrical behavior, including the armature current, back EMF, torque, and speed, was modeled using the differential equation representing by the DC motor's dynamics. So through the simulation result, we can get the key insight into the transient response system stability and potential design optimization before the physical construction. For description and project materials, we use 0.51 mm copper wire, which we made 45 turns on each side. And we use two 9-volt batteries, permanent magnet highlighter casing, which used as rotor core, and paper clips, we use it as the brushes and terminal. And we also use the insulating tape, hot glue gun, and glue stick. For description of assembly works, the copper wire was wound into a coil with 45 turns on each side. Each end of the wire was bent perpendicular to the coil axis, while the wire surface that touches the brushes was scrubbed. This enabled the wires to act as the both axles and commutator segments. Paper clips were bent and fixed in a place to serve as the brushes. And the coil was suspended horizontally between two supports, and the magnets were placed on each side of the coil. So when the battery was connected, the current flowed through the brushes. When the rotor spins, the coil cut through the magnetic field, thus generating the rotation. For testing and result parts, there are 3 parts in this section. So for the first one is experimental setup. The magnet were held in perpendicular to the windings, and it connect the device to 18-volt DC power supplies. And the second part is the measurement and troubleshooting work. We use the visual observation of the motor's performance, and we fix the poor electrical contact, which is the brushes and the commutator, and the coil imbalance. And we also reduce the supporting point friction to make our project more smoothly. So the third part is comparative studies. So through the MATLAB simulation, the result obtained show the expected behavior for torque and speed. Meanwhile, visually observed motor behavior also roughly matched with the simulation trends. Through no quantitative validation could make for the motor speed evaluation.
For the design diagram, we use some of the components to build out a motor hardware. So for the DC voltage source, we use 18 volt as a battery and pass through the resistor, rotational electromechanical converter, and also inductor, and to the electrical reference. And then the rotational electromechanical converter, it connect to the inertia as a magnet and connect to the rotation damper, mechanical rotation reference, ideal rotation motor sensor, to the PS simulating converter and the scope. And for the next connection, we connect to the transient spring to the mechanical transient reference. After we build the simulation diagram, we run the program and it will give the result. So the first graph, we refer to the DC voltage source. We can see that it got damping in the graph, and the second graph is around inductor, so we can refer that inductor not power dissipated, shown in the graph. Next is the inertia graph. We can see that inertia got all damping. So the next graph is the resistor. So resistor also got effect in the motor, which is to protect our component or reduce the current flow. So next is the rotation damper. So for the first graph power dissipated, we can know that the damper is become to the 0, and all the graph shown the damper become to the direct signal. And then the next is the rotation electromechanical converter. So it also show the damper, then after that it become the direct signal. And for the last two graphs, it show the transient spring and the wheel and the X. So it graph also shown the damper, and last it become to the direct signal only.
Next, this is the experiment setup and list of materials that we have used in our PMDC. Firstly, there are two 9-volt batteries and connector wire to connect the batteries to the brushes. Next, highlighter casing as the rotor cord, permanent magnets to provide the magnetic field. Windings, we have used copper wires and the insulating tape to fix the commutators and axles. hot glue gun to fix the brushes, commutator which are also created using the copper wire, and also the brushes that we have made from the paper clip. This is the result of our machine assembly, and here is the video of the machine operation. This is the discussion and conclusion for our project. From this project, it has successfully demonstrated the DC motor principles in a hands-on manner, and despite the lack of measurement tools, the motor performed as expected based on simulation and according to our design assumption. Brush placement, coil quality, and alignment proved to be critical for successful operation. In our project, we have managed to create a basic brush DC motor and successfully built it and tested using low budget materials. From this experiment, we have applied electromagnetic theory and Faraday's law, then designed an equation to create and observe the machine operation. This project has reinforced the practical skills and also the importance of simulation in order to design a consistent and stable machine model. That's all from us regarding our permanent magnet DC motor PMDC, and thank you for watching.